In this video, we are going to talk about some specific subspaces and what happens when we're trying to build functions that go from one subspace to another. And so to do this, we're going to start out by looking at one specific example. This is a really significant example of a subspace. So we're going to start out by looking at what we call the null space of a matrix. And the idea of the null space of a matrix, we're going to go back for a minute into the idea of linear equations, solving linear equations. So the idea of the null space of a matrix is the idea of solving what we call a system of homogeneous equations. The system of homogeneous equations just means that they all equal 0. So here's an example. If we say x1 minus 3x2 minus 2x3 equals 0, because it's equal to 0 and everything has a variable attached, all the constants have a variable attached to them, we say this is a homogeneous equation. We add a second one in, negative 5x1 plus 9x2 plus x3 equals 0. Now we have two homogeneous linear equations. We can write this as A times the matrix X is equal to the 0 matrix, where A is equal to the vector 1, negative 3, negative 2, negative 5, 9, 1. And so we say that the solution set of this system is the set of vectors that make all of these solutions come out to be 0, to make all the equations true. And so we say, given that A, we say the solution set of AX is equal to 0 is the null space of the matrix A. So that's how we define the term null space. So what this means, if we want to think about what this means, we have well, in this case, we have vectors, the vector space that has 3 values in it. And so there's going to be, within our vector space, there is going to be some set of vectors. I'm going to represent them as vectors along a line, that when we take A times any of these vectors, what we do when we take A times that vector is we get, in whatever this vector is, we get the 0 vector in whatever that vector space is. And I'm going to try to draw that a little better. So we get something along those lines. All of those vectors get turned into the 0 vector when we multiply them by the matrix A. And so we can look at an example. Suppose U is equal to 5, 3, negative 2. Then A times U is 1, negative 3, negative 2, negative 5, 9, 1, times U is 5, 3, negative 2. And if we multiply these together, we go across the first row and down the column. So 1 times 5 is 5. plus 3 times negative 3 is negative 9, so 5 plus negative 9 is negative 4, plus negative 2 times negative 2 times negative 2 is 4, so negative 4 plus 4 is 0. Or to write it out, 5 minus 9 plus 4, which is equal to 0. And across the second row and down the column, negative 5 times 5 is negative 25. 9 times 3 is plus 27. Plus 1 times negative 2 is minus 2. Negative 25 plus 27 minus 2 is 0. So u, because if I take a times u, I get the 0 vector. U is in the null space of A. And so if we wanted to show that this is in fact a subspace, we could note that the null space, so let A be any any matrix, and we're using A times x equals 0 to find the null space. So let's assume that U and V are in that null space. To show that this is a subspace, I have to show 3 things. The first is that 0 is in the null space. But to show that 0 is in the null space, all I have to do is take the matrix A times the vector 0, and that gives me across every column and down across every row and down every column, I just get zeros because the 0 vector is just all zeros. So this is 0. So 0 is in the null space. The second thing I have to show is that if U and V are both in the null space, so U and V are in the null space, well, U and V being in the null space means that A times U plus A times V, well, in the null, since U and V are in the null space, A times U is equal to the 0, plus A times V is equal to the 0, which is, in fact, the 0 vector. But what I really need to show is not that these are both the 0 vector and they add to 0. What I need to show is that U plus V for any U and V is in the null space. So I need to show that U plus V, if I take that and I multiply it by A, I get the 0 vector. But A times U plus V is just A times U plus A times V, by the way we've defined matrix multiplication, which is equal to, by what we just said, the 0 vector. So U plus V is in the null space. The third thing I have to show is that C times U is in the null space. So to do this, I take A times C times U. But by the properties of matrix multiplication that we learned earlier, I can rewrite this as C times AU. And since AU is in the null space, since U is in the null space, AU is equal to 0. So this is C times the 0 vector. But a constant times the 0 vector is just the 0 vector. So C times U is in the null space for all constants. This means that the null space is, in fact, a subspace of whatever space it is. To determine the null space, you just have to solve the matrix equation AX equal 0. And we learned how to do that in previous sections, so I'm not going to go through that process. but it is just a matter of solving that linear equation. So you're going to take and find the reduced row echelon form of A augmented with a 0 column. And when you do that, you're going to get a set of solutions, a set of answers. It may be it might just be the 0 vector, but it might also include an infinite family of vectors. Okay, so that's one example of a subspace. This is a particularly important one, is the null space. Another example of a subspace is called the column space. Of a matrix. And the idea of the column space of a matrix is any matrix we can represent as a row of column vectors. And the column space, which we denote as column of A, is just equal to the span of all of those column vectors. And we can do we could go through a full proof of this, but we've actually already done that because we showed in the last video that the span of a set of vectors is a subspace. And since the column space of A is just the span of the columns of A, the column space of A must be a subspace. We could also do this the other way. So we could say the row space of a matrix. We could think of our matrix, this time I'm going to use B, as a collection of row vectors and if I look at these row vectors and I take the span of all my row vectors, then I get that the row space of B is just equal to the span of my row vectors. Now, frequently, before we do this span, we do some kind of let's represent it as columns just because it looks nicer. But either way, it is representing these rows. But so sometimes we take the transpose of a row vector to turn it into a column vector and think about it that way, but it is still the same idea. Okay, so these are all significant ideas. And we can compare and contrast, or I'm particularly going to build a contrasting the null space of A and the column space of A if A is M by N. So M rows and N columns. So the null space of A has, so the null space of A is a subspace of what we call R to the N. So this R to the N is just saying we're talking about vectors that have real numbers, and we have N of them in our vectors. So like R3 would be vectors like 1, 3, 2. 1, 7, 8. Or anything with x, y, z, three vectors in it. R2 would be if we only used 2. And so we can build all of these types of vector spaces as by how many elements or how many items are in each vector in the space. And so this is what we mean by R3. And so the null space is a subspace of Rn. The column space is a subspace of Rm. So the next thing, the null space, you have to find using this null space is found using the reduced row echelon form of A0. The column space is just a span. So the column space is a lot easier to find than the null space. So that's the next big idea. However, we can think of it the other way for if we're checking for a specific vector. So if you have, it is easy to check if V is in null A. All you have to do is show A times V equals 0. When you do that multiplication, it works out, then V is in the null space. It is difficult to show that a vector is in the column space. To show V is in the column space of A, you have to find the reduced row echelon form of the matrix A times, A V to see if it has a solution. So there's some differences between these two vector spaces, these two subspaces. So the next thing I want to talk about is what we call a linear transformation. If you take a graduate level linear algebra class, vector spaces and linear transformations are going to be 90% of the class. And it won't be until pretty close to the end of the class that you see how they relate to matrices. So this is where the theoretical framework behind a vector space comes in. However, it turns out that a linear transformation and matrix multiplication are very closely related. So in an undergraduate class, we start out by learning about matrix multiplication. In a graduate level class, you will start out learning about linear transformations. So a linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector x in V a specific or unique vector T of x in W. And for it to be called a linear transformation, so right now it's just some kind of a function because it takes something from V and moves it into W. To be called a linear transformation, we need two characteristics to be true. The first one, for any two vectors, u and v, if you take t of the vector u plus v, that's equal to t of u plus t of v. So it doesn't matter if you do the transformation before or after you do the addition. And the second one is t of c times u is equal to c times t of u. So scalar multiplication, whether you do it before or after you do the transformation, doesn't matter. If both of those are met, then we say that this is a linear transformation. We define the kernel it's kind of like a popcorn kernel. The kernel of a linear transformation T is the set of all vectors u in V such that T of u is equal to the 0 vector. So this is the idea. The kernel is kind of like the null space. In fact, sometimes it's called the null space of the linear transformation, but usually we use the word kernel when we're talking about a linear transformation. So it's all the things that get turned into the 0 vector when you apply the linear transformation. The range of T is the set of all vectors in W of the form T of x for some x in V. So what that's saying is the range is everything that you can get to from V by applying the transformation to a vector in V. So this is a very theoretical idea, but it turns out that these linear transformations, if I think of a linear transformation on, say, from R2 to R2, so we're going to move from a vector containing two elements to a vector containing two elements. So two numbers to two numbers. That linear transformation can be represented, or another way to think of it is the other way around, with a 2 by 2 matrix. So if I take some 2 by 2 matrix and I multiply it by a vector in R2, I'm going to get a vector in R2. And so this is going to take, this is a rule, so this multiplication is a rule that takes my vector in R2, xy, and gives me a vector ax plus by and cx plus dy in R2. This is a, at this point it's a function, but you can show that this is a linear transformation. That it does not matter whether you take this times, if you do the addition before you do, add two vectors together before you do the matrix multiplication or after, and it doesn't matter if you multiply a vector by a constant before you do the matrix multiplication or after. Either way, you get the same answer. So this is a linear transformation. So everything we've done so far with matrix multiplications and all of that applies to the idea of a linear transformation. So with this, you can think of the linear transformation as generalizing matrix multiplication into other ways, other rules, instead of just this one rule. And I think that's where I'm going to stop with this video.